In Chapter 5-6, we're going to start and look at Part 1, which is line of best fit. And we're going to go over some definitions first. The first one is a scatter plot. It is a way of displaying two variable numerical data where two measurements are taken for each subject. To make a scatter plot, you have two values for each subject that are written as an ordered pair and graphed on a coordinate axes. An example of this would be someone's height and shoe size. So your height is going to be your X value, your shoe size is your Y value. And then, if you would graph this, it would be just a dot on the graph. One thing that I did not mention yet is that you don't connect the dots. So don't connect the dots. I know it's hard because everybody, when you plot a point, you want to connect them together, but we are not going to connect your points or your dots. An outlier, the second term, is a number in a set of data that is far away from the bulk of the data. So it is usually a number that is really big or really small compared to the rest of your data points. So in example 1, we're going to look at the table which shows the predicted annual cost for a middle-income family to raise a child from birth until adulthood. We are given a graph, a table, and we want to draw the scatter plots. Remember, we're not connecting the points. We're just going to graph the points. So I'm going to first start and look at my first X value. So the child's age is the X, the annual cost is the Y. So I'm going to go over 3 and go up to around 10,700. So I'm going to have a point a little under the 11. Next point is X is 6, Y is 11,700. So over 6, up a little below the 12. When X is 9, it is 12,600. So a little between the 12 and the 13. When X is 12, it is 15,000 even. And then when X is 15, the cost is 16,700. So a little closer to the 17. So looking, we plotted the points, and that is it. We are not connecting them. We're just making a scatter plot. And note that it is not a constant rate of change. So there is no slope. So not a constant rate of change. So no slope. So we're not going, up 1,000, over 3, or anything like that. There is no slope for a scatter plot. So part 3, we're looking at relationships. So they can have a relationship or they might not have one. So the first relationship we're looking at is the positive. So notice that the scatter plot, the points are going up and to the right. So that has that positive linear shape. Looks like a positive line. So as X gets bigger, so as X is increasing, so is the Y value. The Y value is also increasing. An example of this would be the more hours you work, the more money you're going to get. So if we work, so more hours worked is going to equal more money. So they're both increasing. As X is increasing, so is your Y. The second one is the negative relationship, and you notice that it has that negative slope look to it, negative line. So as X is getting bigger, the Y values are decreasing. So an example would this be like if you are spending all of your time playing video games, you're most likely not going to be getting all your homework done. So your homework completion rate will be low. And I'm sure somebody can argue against this, but I'm going to use this as an example. So more time spent playing games is less time on homework. The final relationship would be none. So it's just a bunch of scattered points, and they have no relationship at all. So that does not look like a line that's increasing or decreasing. It's all over the place. So an example of this would be the color of your hair and how many siblings you have. There is no connection. So we'll say hair color and number of siblings. So it doesn't matter if you have brown hair. Is not going to tell you that you have two sisters. Or if you have, black hair, you're going to have, twin brothers. It does not matter. There's no relationship. In example 2, we are going to explain the relationship of the data in each example. So in part A, we have television size and price. So as you're looking at your axes, I'm going to look at my x-axis first, my television size. As that is getting bigger, so we're going from 20 inches to 30 to 40, all the way to like 65 inches, you can also see the price, which is your y value, is also increasing, which would make sense. So the bigger the TV, the more it's going to cost. So the bigger the TV, we'll say more money. So it's going to cost more money. So if you have a 72-inch TV, which is really, really big, it's going to cost a lot. It's going to be more than a 40-inch TV. So part B, we have the age and number of pets owned. So this is one of those scatter plots where there is no relationship. Oh, wait, let me go back to A. So this was a positive relationship. So in B, it is no relationship. There's, no connection. Everything is all over the place. So as someone gets older, as their age gets older, the number of pets isn't increasing or decreasing. It's all over the place. So we would say that a person's age has no effect on the number of pets. In example C, we have car price and gas mileage. And as we look at the X, as the X is increasing, so the cost of the car is going up, we can see the gas mileage is decreasing. So this is a negative relationship. And we can say that the more expensive the car is, the gas mileage is going to decrease, which makes sense. Like if you think of like your gas guzzlers, your SUVs, your big trucks, these are the Chevys that we're talking about. The bigger the car, the more expensive it is, and, it's not going to have as great as gas mileage as a smaller car. So, more expensive car, decrease in gas mileage. The final definition we're going to look at is the line of best fit, and this is a line that represents data on a scatter plot. It's used to make predictions or describe the data, and this is something that is used in science a lot. It's used in business. It's used all over the place. So example 3, we are going to plot the points, and then we're going to find the line of best fit, and then we're going to find out what is the equation for that line. So first we're going to plot all of the points. Once the points are plotted, you are going to draw a line of best fit. Now remember, this is not going through all the points. You are going to draw a line through the middle of your points. So if you look at the line that I drew, and I apologize, it's not very straight. It's hard to do that on an iPad. There are about the same number of points almost on the left and the right sides of the line. So you want to make sure you're in the middle of those points. So now we are going to write the slope-intercept form of the equation. So if you recall, that is y equals mx plus b. So we are going to identify the slope and the y-intercept. So what you're going to want to do is pick 2 points that are on the line that you drew. So if I zoom in here for a second, I have 2 points on my line that were at 2050 and 3060. So 2 nice points, these lattice points, on the line. And you may have something different, and that is okay. It's a line of best fit, so everybody might have a different equation. It should be somewhere in the same area, though. So I have those 2 points. I can make a slope triangle with that. I can see that I'm going up 10 and over, what is that, 10. So you got to be aware of your scaling. So the y values were going up by 10, and the x values were going over by 5. So I'm going up 10 over 10. So my slope is going to be a 1, and I found that by doing a slope triangle. And now I'm going to use one of my points. So I should write my points down. What did I say? It was 20, 50, and 30, 60. And again, you could have 2 different points. So I'm going to use my x and my y here to plug it into the equation. So we'll have 50 is equal to 20 times our m, which is 1, plus b. So 50 equals 20 plus b, subtract 20. So my b is going to be 30, which matches up pretty close to my line of best fit. So y is going to equal x plus 30. So this would be my line of best fit. And again, it does not have to be exact. It has to just be close.